Here is a number that changes the way you think about modern technology. 5 minutes. That is all it takes. 5 minutes from the moment a truck parks at a test range in China to the moment 96 autonomous drones are in the air, a target has been identified without a single human making the call, and a precision strike has been completed. No pilots, no manual targeting, no command center full of analysts working through a checklist. One operator, one screen, 96 machines doing the rest. This is not a simulation. This is not a classified program that someone leaked to a journalist. On March 25, 2026, Chinese state broadcaster CCTV aired the footage in full. The entire operational sequence, launch, reconnaissance, target discrimination, precision strike, broadcast to anyone in the world who wanted to watch. The system is called Atlas. It is built by CETC, China Electronics Technology Group Corporation, one of the country's largest state-owned defense technology organizations. And what it demonstrated that day is forcing engineers and analysts around the world to ask a question that does not have a comfortable answer. Are the air defense systems the United States has spent decades building and hundreds of billions of dollars perfecting, designed for a threat that no longer looks like the one that just showed up? Let's go through exactly what happened, how the technology actually works, and why the engineering gap this demonstration revealed is genuinely difficult to close. Atlas is not a drone. It is a complete, self-contained autonomous strike architecture. Road mobile. No runway required, no permanent base, no specialist crew needed to set it up. You drive it to a location, deploy in minutes, and it is operational. The system runs on 3 vehicles that work as a single coordinated unit. The Swarm 2 is the launcher. From the outside, it looks like a standard heavy military truck. When it activates, the rear section opens to reveal rows of launch tubes stacked in a grid. A single Swarm 2 carries 48 fixed-wing drones, all preloaded, all ready. 2 trucks working together put 96 drones in the air from one road mobile package. The Swarm 2 made its first public appearance at Airshow China 2024 in Zhuhai, an open commercial aviation event attended by international visitors, industry representatives, and journalists. This was not a classified reveal behind closed doors. It was a public debut at a trade show. The command vehicle is where the single operator sits. One person, one screen, overseeing the entire operation. The operator does not individually pilot each drone. At that scale, that would be physically impossible. Instead, they define the mission parameters, the target zone, the objectives, the operational boundaries. The system takes over from that point. The operator functions as a supervisor, not a pilot. The support vehicle manages communications infrastructure, system health monitoring, and field logistics, keeping the entire network connected and functional, regardless of terrain. CETC, the organization behind Atlas, employs over 200,000 people across electronics, communications, radar, and AI systems. This is not a prototype built by a small research team. It is the product of one of China's most significant and longest established defense technology institutions. Here is something that surprises most people when they first encounter this story. China did not develop Atlas in secret. CETC ran its first experimental large-scale drone swarm in 2018. The results were documented in Chinese aerospace and defense technology journals, publications that are publicly accessible. By 2023, U.S. defense analysts were actively reviewing those journals, trying to reconstruct the direction and pace of the program from open sources. In 2024, the Swarm 2 launcher appeared at a public air show. In March 2026, the complete operational sequence ran on national television. 8 years. From the first experimental swarm to a fully demonstrated autonomous kill chain. every major milestone documented, publicly visible, and reported on by international defense analysis communities. The development timeline matters because it reveals something important about the nature of the program. This was not a crash effort driven by a sudden technological breakthrough. It was a methodical, phase-by-phase engineering progression. Algorithm development, hardware refinement, integration testing, scaled demonstration. The kind of timeline that reflects serious institutional commitment over the long term. Now let's get into what Atlas actually did on March 25th, because the technical sequence is the heart of this story. At the test range, 3 ground vehicles were placed in the strike zone. They were visually identical from above, with the same dimensions, the same shape, and the same color. It was a standard decoy setup, the kind designed specifically to defeat targeting systems that rely on visual recognition. Atlas did not rely on visual recognition. The system launched reconnaissance drones first. They spread across the target area and began collecting data from multiple positions simultaneously. It was not imagery for a human analyst to review, but raw data, electronic emissions from each vehicle, antenna activity, movement signatures, and the behavioral profile of each target, rather than its physical appearance. This data fed continuously into the AI algorithm running at the core of the system. The algorithm cross-referenced inputs arriving from multiple drone positions at once, building a composite picture that no single vantage point could have produced. It identified behavioral patterns consistent with an active command vehicle, specific electronic characteristics that a passive stationary decoy simply does not produce. Once the algorithm reached sufficient confidence in its target identification, it initiated the launch sequence. The Swarm 2 opened. Drones deployed at intervals under 3 seconds each. In flight, each drone received continuously updated targeting data from the network and locked onto the designated vehicle. The operator did not select the target. The operator did not guide the munition. The system handled both autonomously. That is the technical achievement the March demonstration documented. To understand why Atlas creates a genuine engineering challenge for existing air defense systems, you need to understand what those systems were actually designed to handle. The Patriot missile system entered U.S. Army service in 1984. THAAD, Terminal High Altitude Area Defense, achieved initial operational capability in 2008. Both were engineered around a specific threat model: ballistic missiles, cruise missiles, and manned aircraft. Relatively small numbers of incoming objects following predictable flight physics. These are exceptional systems within their design parameters. Patriot has intercepted ballistic missiles in real operational environments. THAAD is purpose-built for exo-atmospheric intercepts of ballistic threats. For the problems they were designed to solve, they remain among the most capable defensive systems ever built. But Atlas presents engineering problems outside that design envelope. First, volume. 96 simultaneous airborne contacts. The track management, radar processing, and engagement sequencing required to handle nearly 100 small autonomous objects appearing at once is a fundamentally different computational and mechanical challenge from what Patriot or THAAD were architected for. That is not a criticism of those systems. It is a description of their original requirements. Second, flight profile. Small fixed-wing drones at low altitude create a detection problem rooted in basic radar physics. Terrain features, hills, trees, buildings, and the curvature of the Earth itself produce radar shadow zones at very low altitudes. A small drone flying close to the ground can remain below reliable detection range for much of its flight. This limitation has been documented in radar engineering literature for decades. What Atlas does is combine low-altitude flight with high volume simultaneously, turning a known physical constraint into an operational challenge. At a scale these systems were not designed to manage. Third, cost-exchange ratio. Advanced interceptor missiles represent substantial per-unit manufacturing cost. When a high-cost interceptor is used to engage a low-cost autonomous drone, the production and logistics math becomes a sustained problem across a long engagement. Defense economists and military planners discuss this openly in published analysis. It is a documented concern, not a theoretical one. The defense engineering community is actively working on responses, and it is worth being specific about what is actually in development. The most technically promising counter-swarm approach is directed energy. High-powered laser systems can engage multiple targets near simultaneously. They do not have a finite magazine. They do not need to reload between engagements. The per-shot cost, once the system is built and powered, is electricity rather than precision munitions. That physics makes directed energy conceptually well-suited to the saturation problem in a way that conventional interceptors are not. The U.S. Army's Indirect Fire Protection Capability Program, IFPC, includes directed energy components specifically developed against drone threats. DARPA has multiple active counter-swarm research programs. These are funded efforts with engineering teams working on real hardware. The remaining challenges are practical rather than theoretical. Effective range under real field conditions, atmospheric effects on beam coherence over distance, power generation requirements at operational scale, and the thermal management needed for sustained continuous use. These are solvable engineering problems. The timeline for solving them and deploying the resulting systems at meaningful scale, however, is measured in years. One aspect of the Atlas demonstration that deserves more attention than it usually gets. CETC did not have to broadcast this on CCTV. China's defense industry regularly tests systems that never appear on state television. When full operational footage is broadcast publicly, that is a deliberate institutional decision. CETC is a commercial organization with international customers. Public demonstrations of operational capabilities serve documented purposes, establishing technical credibility, generating export interest, and influencing procurement evaluations by other nations. The Swarm 2 debuted at an open commercial air show, attended by defense procurement officials and industry observers from dozens of countries. The CCTV broadcast extended that communication to a global audience and established on the public record that a complete autonomous kill chain had been demonstrated, not claimed in a press release, demonstrated on camera. When a capability is shown publicly, it forces every other nation's engineering and procurement community to formally assess the gap between what was demonstrated and what they currently field. That assessment drives funding requests, accelerates development timelines, and reshapes procurement priorities. A public demonstration functions as a strategic communication instrument operating through the engineering and budgetary processes of every government that watches it. Atlas, as demonstrated in March 2026, is a first-generation system. First-generation systems always produce successors. Swarm AI algorithms improve with operational data. Every test, every demonstration, every simulation generates information that refines target discrimination accuracy, improves formation coordination, and reduces decision latency. The system that ran in March is not the system that will exist in 5 years. On the hardware side, Huawei is publicly documented to be mass-producing the Ascend 950PR, an AI inference chip optimized specifically for edge computing workloads. That is precisely the processing architecture autonomous drones need to make targeting decisions in flight without depending on continuous communication with an external server. More onboard processing capability means more operational independence and more resilience in signal-contested environments. Manufacturing scale drives cost down along a well-documented curve. Larger swarms, hundreds of coordinated units rather than 96, are a logical extension of the same software and network architecture already demonstrated. The command vehicle that managed 96 drones is fundamentally a software platform. Scaling the number of coordinated units is an engineering problem with a visible engineering solution path. Here is what March 25th actually established. Not that existing systems are obsolete, not that the engineering response is impossible. It established that the gap between what was demonstrated and what is currently fielded is real, it is documented on camera, and it is not closing by itself. Systems engineered for ballistic missiles and manned aircraft were not designed for 96 simultaneous small, autonomous contacts coordinating through an AI-driven network at low altitude. The engineering response, directed energy, AI-driven defense processing, counter-swarm software, exist in active development programs with real funding. But development, testing, and deployment at scale takes time. The timeline is the central question every defense analyst and procurement official is now working with. The footage from March answered whether the gap exists. The question that remains is how fast it can be closed. If you found this breakdown useful, subscribe for more in-depth coverage of defense technology and engineering. Drop a comment below. If you were designing a counter-swarm defense system from scratch today, where would you start?